Thank you. Thank you for having the opportunity to give a short presentation of what we are doing. I just jumped in this open slot, but yeah. So as said, I'm Rainer Wansch. I'm from the Fraunhofer Institute for Integrated Circuits, which is based in Erlangen, Germany. So we have plenty of sites. I'm in the Erlangen site where I'm with the Communication Systems division, and in this division heading the business field of satellite communications. There's plenty of other divisions within the institute. There's also some dealing with non-destructive testing, positioning, networks division, supply chain services, but we also do integrated circuits as well. So it's not only the name, we also have a division really dealing with, they call it smart systems and electronics, but they really do ASIC design and use, let's say, what's publicly available in different foundries to produce these things. And in our division, we have like 4 departments. One I'm also heading, that's the RF and SatCom systems department, a broadband and broadcasting department where we closely work together, especially on the 3GPP, NTN type of things. Radio communication systems, they are more dealing with, let's say, defense communication systems, and the electronic measurements and signal processing, which is based in Ilmenau, a little bit north in Thuringia. So we are very well present in Bavaria and Thuringia, and also with a division in Saxonia, so quite distributed. So what we are basically doing, our core competencies is we start from designing, mostly in the vision of application-oriented communication systems. So nothing from scratch, which is, I don't know, providing the last tenth of dB for a certain solution, but really looking at what's needed, what kind of application needs, what kind of requirements, and then we try to build this in prototypes and also go into test beds to figure out if this can be used in real life. So that's always the target, building up test beds and building up something where one can see things are working or not. So next to satellite communication, we also have 5 other customer and business focus. One is automotive, where we started with a lot of, let's say, IP developments and software developments, which are in most of the cars in DAB receivers. Currently going more in the direction also in 3GPP, NTN. We work together with the 5G AA, which is the Automotive Association inside that, and figuring out what the requirements of the automotive industry really is for NTN in the next years and in the coming years. Artificial intelligence, which is, let's say, more a tool, but we do neuromorphic hardware, we do different AI for spectrum sensing, spectrum resource management, Internet of Things. That's one part where we developed something better than LoRaWAN, which was mentioned before. That's something I will go together with satellite communication in detail later in this presentation. And then we have the mobile broadband communication, which is very much related to 3GPP. And with 3GPP and satellite comms, we work together on all these NTN kind of things. We also contribute to the standards, go to all the standardization meetings, which is a lot of effort, but we try to substantiate that with also our own IP, which then can bring us some revenue in that direction. And public safety, that's everything which is to be done with the German Department of Defense, where we are working with. In satellite communications, our main topics are system consulting and definition of different satellite communication systems in almost every orbit, so from LEO to GEO, very low LEO, MEO, everything which is needed there, where we also, thanks to a contract with ESA, we built our own constellation simulator, which can provide throughput data, interference between the systems and all these kind of things. Then on system development, as said already, the main topic, satellite integration in NTN, in 3GPP, 5G, IoT over satellite, where we use a terrestrial waveform, which can then be directly used for satellite. So you don't need to change anything at the transmitters. They also can operate with satellites in that direction. And some work we did a lot in high throughput systems, which is now quite decreasing, to be honest, where we built, especially for DVB S2X, some beam hopping features, doing the super framing format and all these kind of things, establishing also there some testing equipment so that you can really figure out if beam hopping could be of use, and if receivers and transmitters and the satellite systems work properly together, because you have some timing issues inside that and you have to compensate for that. Another topic, antennas for satellite communications. Antennas we do especially currently also with two ESA projects for the satellites, for CubeSat type of satellite, so making a Ka-band satellite antenna tile, so which is 10 by 10 centimeters, but then this can be placed next to each other, and you can create larger antennas out of this, which is a nice thing, which has a little bit the drawback if you want to use existing phase shifting devices. The market for satellite is not that large, so there's only one available. On ground you have plenty of them, maybe 5 to 10, but for satellite there's only one currently available, and we need to use this. But once we have like this antenna for the satellite, changing the phase shifting devices, that's the easier task than creating a new phase shifting device. Yeah, transmitter receiver components, mainly based on software defined radio systems. We do full system demonstrations for all these different applications. And we have a small regenerative payload processor on the German Heinrich Hertz mission, which is available for experiments, so you can do something in Ka-band up and downlink, and also reconfigure, regenerate the signals on board of the satellite. It's maybe not up-to-date FPGA technology, because I started this project in 2009, so some years ago. And the decision for the devices also has been a little bit earlier. Now more modern devices are more capable on what we have on board the satellite, but still we can provide something there. Especially what we did was a telemetry and telecommand system integrated in the communication link, because the normal telemetry and telecommand link, which is provided from the ground station for the satellite, it's not capable of enough. So if you want to upload a new firmware, which is some megabyte, going over a 500 bytes per second link is nothing one would do. Therefore, we did our own in that direction. So the main business topics, program lines we are working on, NTN, SAT 5G. I have the chance tomorrow, being on a podium, maybe we can discuss a little bit more on that tomorrow. High throughput systems, as already mentioned. Antennas, I also already mentioned more or less. Onboard processing, and NTN. There's another ESA project we are working on, which is called the 6G Lino. That's satellite demonstration providing end-to-end communication with a G-Node B on board. So the hardware is built by GSAT. We are doing all the programming for the G-Node B. The satellite itself is built by Open Cosmos, and University of Surrey is also involved in that project. So a nice project, hopefully with the launch of the satellite in early 27. So we are looking forward to it. And with this project, there's some first experiments already involved inside the project, but after the project is finished, this is also available as a test vehicle in space to do some 5G, 6G testing kind of things. That will then hopefully run over us, and we can build the connection to that. So what we are doing in satellite IoT. So I think most of the points already have been mentioned in the panel and in the presentation before. What we are using is a special waveform called MIOTI or TSUNB. That's the specification which is done with ETSI. So there's an ETSI standard called TSUNB, TS standing for telegram splitting ultra narrowband. That's what it's done. This comes from terrestrial applications, so from meter reading, more or less. So having small devices also placed in the basement, and you can then achieve coverage of 10 to 20 kilometers with 10 milliwatts of power and battery lifetime, if you only send twice a day or something like that, for 10 years. But still, that's a good thing. And that's the basis what we are using. So there's plenty of chipsets and installations or nodes available, and we just can use it or try to use them also for satellite applications. That's how it's more or less set up. So you have different sensors. Currently, they are transmit only. So there's no downlink, it's uplink only, making it fully uncoordinated. With the satellite coverage, if you would assume one coverage, we can get a throughput of, I think it's 2 or 5 million messages per day. Much more than LoRa can provide, but that's a different story. There's also some investigation studies on what LoRa can provide and where MIOTI has its benefits. But let's say the application is always large areas where you don't have any terrestrial available connection, or your devices are too distributed to install a base station, where that's the application case. And one of these applications, that's something we totally different to what one would maybe assume. That's the so-called Gaia initiative, which we started some years ago, doing wildlife research and conservation with AI and satellite-based IoT technology. So the satellite IoT-based technology, that's coming later than based on MIOTI. So what's the aim for this? That's together with some partners which are below there, funded by the German aerospace agency, for the German space agency. Rapid Cubes building satellites, so the small satellite manufacturer, and the Leibniz Institute for Zoo- und Wildtierforschung. I don't know the English word for this yet now. But that's the wildlife researchers which are out there in the field and doing these kind of things. Why do we do this with AI and satellite, and why wildlife research? So it's always good to have protection of the Earth's ecosystem. There could also be some tsunami warning by elephants and chickens that has already been done. What we are aiming for is more vultures, equip vultures with these kind of things, and you can also do detection of animal pandemics with these vultures, because they go everywhere where dead animals are, and that's what we use there. And then we use all three different intelligences which are inside that system. So the human intelligence, the animal intelligence of the vultures, and also some artificial intelligence, which I come later to. Why do we use vultures? So one is they are little researched, and they are really one species which is in danger. Then if you look at these violet lines, that's some vultures flying large areas. So you have with one vulture already like 1,000 kilometers north-south, and maybe also the same dimension east-west. So they are really covering large areas. And you also use the swarm intelligence of them. So they fly wide, in a wide distance, but still they can detect carcasses very, very fast. They have a very good visibility still from 4 kilometers or like that, and they communicate over some kilometers or tens or hundreds of kilometers. Nobody knows how, but they do it. And then they come there, and whenever there's a large animal, there's a lot of vultures, and that's something we will use. Why do we do this? One very nice thing is if you as an engineer suddenly work together with biologists, that's a different point of use, and that's really exciting to do this kind of things, really having totally different, seeing them in main of the application, as you saw before, is in Namibia, running around in the Etosha National Park, and equipping vultures with these kind of devices and all these kind of things, that's really impressive. And clearly, satellite communication is involved. That's why we are inside that. So that's our main part. And then we also worked on or still working on distributed computing and AI, because you use, once there's a large animal, there's many of the vultures. So if you have many of the vultures equipped with some of these devices, you could also use this to generate kind of a small network where you can distribute some of the functions which you want to do with AI. That's in principle what the vulture carries with it. So there's this so-called split tech camera in the front, a small satellite transmitter on the back with some additional electronics inside, so some acceleration sensors, GNSS sensor, all these things are inside that. The vulture approaches a dead animal and eats, so you detect what the vulture is doing. So you don't switch on all the electronic inside this thing all the time, because that would be too power consuming. Therefore, you use the acceleration patterns which the animals create when they do different stuff like flying, sleeping, I don't know, eating. And once they are eating, then you switch on things. When they start eating, you switch on the camera. The camera takes a small picture, figuring out which kind of animal is there. The onboard AI classifies this animal, so saying it's a zebra, or it's an antelope, or it's a rhino, or it's an elephant. If it's an elephant or rhino, then you switch on the satellite communication device and just deliver, hey, we found the vultures are eating a rhino at a certain position. And then comes the human intelligence into play. So this goes to the rangers, and then they can say, okay, we drive there and figure out if this has been died because of illness or age, or if it has been poached. And that's when things can be done in that direction. So yeah, I already said that. So the guys from Leibniz, they do all this wildlife observation. We did the embedded AI and the IoT and the tag, and RabbitCubes is building the satellite with MyOT transmission. How long do I have? I have 5 minutes. Huh?
5 minutes if you want to ask.
Okay. Yes. As already said, so we currently figure out if we can use the hardware as on ground. So that's ISM band 868 megahertz. If this can be still used for satellite, that's something within a new program we will figure out which is the best to use. That's how it looks on the vultures. And then what we are doing if there's more than one vulture, so we can also distribute this image classification over several of them. So they span an ad hoc network, which can be volatile, so you never know if one vulture still stays there and everyone stays there, and if you organize it with a central node and the central node flies away, then you are lost. So therefore, we also built these kind of volatile swarm intelligence project that was done in a different project, but with this ad hoc networking, which you can see here, so you can distribute different functions between the birds. That's what we also try to do, not with birds, but with drones, for example. So we don't rely on, let's say, the physical layer is transparent for us, so we have our system running above this, and this then can also be used for drones. And also in drones you have some use cases where some get lost, and you need to figure out that things are still working. And the next step is now to bring this into space with a small satellite. And that's hopefully starting next year. We almost had the project in, I think it was in September, October, but then the German government said we don't want to be in charge anymore, and then also the funding of this project failed in that direction. So yes, and then I would be open for some questions, maybe some point of how you can work together with Fraunhofer. So what we very much like is contract research with clients. That's also where Fraunhofer is really directed at. Collaborative research, maybe funded by EU or some of the governments. We do consulting services, and we also do patent technology or product licensing. And that's it. Thanks for your... I'm open for questions.
Hi, sorry. Lawrence Russell, Data Center Dynamics. Have you done any work around quantum key distribution? Do you have any awareness of how you could create quantum-aware communications in the future world?
We personally not, but there's one quantum key distribution. We have the Institute for Optics and Fine Mechanic in Jena, and they are very much working on this with entangled photon sources. We don't do any security things, security, that's security. Things currently that's done by post-quantum things, that's nothing we do currently, no. Yeah.
Sorry, Andy Love, Airbus. I'm just curious, the analysis you're doing right now, is that based on RF data from the transmitters from the vultures? Or are you using existing Earth observation data that you're buying in as a service as well?
So the vultures itself are the sensors. So they carry the camera, and you do all these evaluation of the images on board the vulture. Okay. So satellite is only for distributing the RF signals from the vulture to a certain ranger station. Yeah. No, currently this is all based on RF. Just RF. GSUNB has like 200 kilohertz of bandwidth, and with that we can receive like 5 million protocols per day. Yeah. Yeah. Protocols are very small. We also want to be very power efficient in that direction, so it's like 200 bytes, something like that. So really not, we don't want to distribute any picture from the vulture via satellite to a ground station or to the ranger. So really everything is already calculated and you only send the information. That's a rhino or not. Yeah.
So are you doing edge processing then? Yeah. You're not taking the raw data and doing the processing, you're doing edge processing on that.
We call it extreme edge processing because it's really low power and let's say low capable device. That's all based on microcontrollers.
Okay.
So and the picture size is maybe like smaller than VGA. So yeah.
I think we've got time for one more question. If
Renato Goodfellow, Commercis. Can I ask, from the work you've been doing and supporting with nature, have you succeeded, or any other party, in making a positive business case to see that the investment cost is recovered in the benefits delivered?
Not yet, no. No. This was really based on public funding. So yeah, to be honest. So, but what the nice thing with this is, it's a very nice use case and a very, let's say, nice to transport use case. And once you have some satellites in space, it's easier to get to additional use cases and deliver these kind of data. Yeah. And as we use the MIOTI system, there's also there's a MIOTI alliance behind. So from, I don't know, from, yeah, the basic equipment manufacturers really to end-to-end to the guys who provide the data via some cloud services. And once you have this, you can just, that's at least that's our aim, to jump on this train and having them helping us to introduce this IoT system. Yeah. Yeah.
How are you going to pass all this into a product that can be sold? Because while you were talking, I was thinking of how can we use it?
Yeah. So the product itself, let's say the transmitter device and all these kind of things, that's based on commercially available electronics. I don't know, costs $2. If you stick with 868 megahertz and don't want to have, so we can close our link with maybe 100 milliwatts. And then you have cheap devices that's already available. You could even use the LoRa devices and reprogram them to our system. That could also be possible. So that's available. What we mainly need is the satellites. And we also are in a lot of discussions with all the guys mentioned before, more or less, like FOSSA, Connected, Plan S, I don't know who else, that our receiver fits on a Raspberry 4. So you just need to do a Raspberry 4 on board the satellite and some additional antennas in the front end. That's clear, yeah. Yeah. So from that respect, I think it's quite well possible to introduce this also commercially, but you need to have the certain use case, and then it's more the sensor, not so much the transmitting or let's say the communication system. It's mainly based on the sensor and the device you want to introduce there.
Heiner, thank you very much.
Thank you.